My name is Matthew Fisher. I'm submitting Challenge 1 for ECE 561, Section 001 at NC State University. This is a video to prove the functionality of the challenge for the board isolated from the debugger. The board is currently plugged into the computer. I'm going to run the debugger and program the MSP432. And now the program counter is sitting in main, waiting to be ran. So I'm going to stop the debugger now that the MSP432 is programmed. I'm now going to unplug and plug back in the MSP432. And here's the board. So, testing functionality. This button causes the watchdog to reset, which flashes the LED for 1 second. If I push and hold, the watchdog is constantly reset. And if I push the hardware reset button, the board itself will not flash the red LED because the watchdog did not cause the reset. I'm going to push the reset button one more time. And from this moment, 1 minute from now, the memory should write, which should cause a green LED to come on. And this completes the video showing the functionality of Challenge 1 for ECE 561 at North Carolina State University.
Hello, my name is Matthew Fisher. I'm a student at North Carolina State University. This is the course ECE 561, Section 001. I'm going to be going through the code and explaining the functionality for Challenge 1 of automated main memory programming with the watchdog timer enabled. So starting from the very beginning, this is a buffer size that I'm using as a constant value within the code. This buffer size is just a constant value I'm representing for one sector. Within main memory there are two banks, bank 0, bank 1. Each bank has 32 sectors, and so therefore I'm programming in 4 kilobyte chunks, so I'm programming one sector at a time within bank 1 of main memory, and I'll get more to this in a little bit. The data that I'm programming is a hex value of 01, so the pattern is a 01 pattern. And I'm using the data inside this buffer to program, like I said, one sector at a time. This is up mode config. I'm configuring, since I have an interrupt, timer is 0. This is the configuration for that interrupt to work in up mode. I configured the timer to run off of A clock, which is set to 32768 kilohertz. I've got the CCR0 capture compare register essentially capturing every quarter second of that value. So 8192 is a quarter of 32768. I'm enabling the timer A interrupt and the capture compare register interrupt. And I tell the timer to clear once the CCR value has been met. Going through functionality of main, this is the almighty while loop essentially, and the functionality of the program. Memwrite is a variable that I'm using to keep track of how often memory is written. So 81 or 184 quad 0 is a value that I've used using count events. So if we go to debug mode, and count event right here, these count events can be used with a breakpoint to test functionality for cycles of operation. I simply just chose the value based on cycle of operation by setting a breakpoint and simulating that way. So starting from the very beginning, I disable the watchdog. This is just to make sure that the watchdog doesn't fire during the initialization process until I tell it to configure the watchdog here. I then initialize the ports. First, I set the direction bits. First direction bit, I make sure that the button that I'm using is set as an input. I then toggle essentially the direction bits for port 2 for pin 1 and pin 0. It's for the green and red LED to operate as intended. I then set the resistor enable for the button so that it's pulled up when it's not pressed. I then set the output register for port 1 and port 2, and essentially sets the resistor to be a pull up. This enables it, this sets it. And this just turns off the LEDs to make sure that they're not on during the initialization process itself. Next, I configure the clock sources. I set both M clock and A clock to their respective oscillators to make sure that the functionality is as expected. This is turning on vCore 1, which is the higher power level needed to run at 48 MHz. I program memory at 48 MHz and then set the clock back to 1.5 MHz for normal operation. And I do that so that flash memory is programmed as efficiently and effectively as possible. This is setting the DCO frequency, the oscillator, to 1.5 MHz. This initializes M clock to be the DCO clock that I set. This sets A clock to the ref 0 oscillator, and this sets ref oscillator to 32 kHz. Next, I have a function called check timeout. This checks the functionality for the watchdog timeout event. So to prove functionality that the watchdog is causing the red LED to flash based on only the watchdog being set itself, I'm using the reset control hard reset stat register, and I have functionality to prove that feature. For hard reset, watchdog timer A timeout has a reset source number of 1, and if we go over to here and then up to our reset control register, we have hard reset stat register here, which is what I'm using right there. And if we go here, this is the SRC1 value, which represents the watchdog reset source number here. And again, this is a hard reset, so simply go to the reset hard reset status register. This is the bit that I'm checking because it indicates that the watchdog itself has set a flag saying that it has timed out. So we go back to the code, and that hex 2 value is just bit 1 of the reset hard reset status register, which is that resource number as indicated earlier. If this is true, the watchdog timeout has occurred. I then toggle the red LED. And toggle red LED is simply just a simple counter. It starts at some initial value based on the M clock value and counts down, setting the bit high and then low. And this is a 1 second blink as required. Once this has occurred or check timeout has happened, I'll always make sure that the flag for that particular value for that timeout is always cleared. And this is mostly for functionality to make sure that the red LED only blinks accordingly whenever the watchdog times out. This function configures the watchdog. I disable all interrupts. I then force the watchdog into hold mode, essentially temporarily disabling the watchdog so that it doesn't actually fire in configuration. This is just for proper programming etiquette for the embedded processor. You halt it before you program it. I have 4 flags I'm using to set the watchdog. I have the A clock source. I have the 2 to the 15 divider, which is for 1 second based on A clock. Excuse me. I have the, I'm sorry, WT, this is the password here. A clock is this flag. The divider is here. This divides it down to 1 second when A clock is chosen. And finally, this one is the control clear register. Since this just clears the watchdog counter value to 0, and this essentially a functionality wise is the same as called kicking the dog, and this essentially is what causes the watchdog to keep from resetting or having overflow bit into that reset control register, which I mentioned earlier. Once the watchdog's been configured correctly, I then re-enable master interrupts essentially. And it's just, like I said, these two are just for good programming protocol. Configuration of timer A0 is next. This essentially configures the timer A into up mode. I'm using the timer to kick the watchdog. That's really its only functionality, is every quarter second I have it resetting the watchdog essentially automatically. So once it's been configured in up mode, using the up mode struct which I mentioned earlier, seen here, it's every quarter second. I tell essentially that I want CCR0 interrupt enabled for this, and I want it to use this function handler here. This function handler is a function pointer to, like I said, reset the watchdog, kick the watchdog by clearing its value, and all I do is simply then is just clear the capture compare interrupt itself to make sure that it can then be triggered once again as needed. Next is enabling the capture compare interrupt during the initial process of timer A0. I then enable interrupt for timer A0. This starts the counter itself for timer A0, and this enables all interrupts for the board once it's been correctly configured. Once everything essentially is initially initialized, the main program starts. So this is just pin toggling essentially. I'm checking directly whether or not the button has been pressed. So if the button is pressed, it registers a short, essentially a 0. While it's pressed, I stop the timer, which causes the interrupt to no longer be fired, which no longer clears the watchdog timer, and therefore the watchdog can count up to its value and then overflow. And when that bit is overflowed, it then causes the flag to be set in the reset control hard reset register. And this just disables the interrupt for that timer to make sure that not only the timer is stopped, but the interrupt itself is disabled. Once that happens, I then check the timeout value, and check timeout essentially is checking the value as we went through earlier here. This functionality is going through memory write. So I set a breakpoint and I check whether or not the cycles themselves in this particular while loop occur for one round, and I just do a little bit of math, and it's real simple to use the 1.5 megahertz clock to get this value which I'm comparing against for 1 minute time intervals. Once 1 minute has passed, I clear the memory write value, and I tell it to write to flash, and then toggle with green LED. Real quickly, the toggle green LED is just like the red LED, and functionality, nothing is different. I have a set value based on some 35 cycle count value, which again is checked the same with the breakpoint and the count event, and it just toggles the green LED for 1 second per the specifications. Write to flash. This is the last function for the functionality of the program. Write to flash occurs by starting at bank 1, starting at hex 20,000. That's based on documentation for here. Right here, we have main memory and information memory. I'm programming main memory, and I'm accessing hex 2 quad 0 to 3 quad F, and this represents bank 1. This next function is essentially populating the buffer with the data as specified in the beginning of the program. Next, I set the DCO frequency to 48 megahertz. This is essential just to make sure the programming of the flash is done as quickly and efficiently as possible. I set the wait states for bank 0 and bank 1 per the specifications of the data sheet, and this is to make sure that the flash memory can be read correctly, and it's based on some synchronization processes for the main clock to flash as well. I unprotect the sectors, all sectors at once, using shorthand notation. There are offsets for each bit, but I'm programming all 32 sectors, so each F is 4 bits of ones, so there are 4, 8, 12, 16, 24, 32, 28, 32. Yes, so the 32 total sectors, I'm just representing them as Fs and hex. It's just shorthand notation from protecting all the sectors for that particular bank. This is the perform mass erase function through the API. Any sector that's unprotected will get erased. So I unprotected all the sectors for bank 1, and then perform mass erase on those unprotected sectors, and that essentially writes all Fs to main memory bank 1. I then program in 4 kilobyte chunks here using the program memory of that buffer that I mentioned and the buffer size specified. And then I just offset up 4096 bytes each bank location and do this 32 times to program it. I then protect the sectors again once I'm completed all my writing needs, and again it's a total of 32 sectors based on 4-bit offsets. Each F is what that represents essentially. There are flags in API, but I just hard-coded it to be all Fs. And then I set the clock back to 1.5 megahertz once I'm done programming the right memory. And quick note, I know that if ever any of these particular ones fail, and it has this while not feature, these programs fail with a false. So if this were to fail programming, it would fail with return a false, and it would get stuck within this while loop. When you get stuck in this while loop, the watchdog itself, essentially the program would no longer complete. So that's essentially how I make sure that everything's programmed and verified accordingly. It would never flash a green LED if it failed, because it would get caught within this while loop here, and the program would never complete its way through. And essentially this completes the explanation of my code for challenge 1. I want to thank you very much for your time, and have an excellent day. Hi, my name is Matt Fisher. I'm a student at NC State University, and this is the last section of the video for challenge 1. This is proving correct memory programming of the value that I expect for data for challenge 1 in ECE 561 section 001. So I'm going to first begin by decrementing this value, which was originally explained. And this is so that memory writes a little quicker than 1 minute, save time for everyone. I'm going to also begin by debugging the board and saving the changes. Okay, the program counter is now sitting at the top. I'm going to tell it to go. And I have a breakpoint set at main memory write to flash here. So it's ready to write, or erase, I'm sorry. So in memory browser, here is the beginning of sector 0 for bank 1. I'm now going to write from hex 20,000 to hex 3 quad F. I'm going to do that by showing here that a sector can be programmed successfully. And now they have shown red since it has changed, and it is exactly 1 sector size from 20,000 hex to 200 F0. And this occurs 32 times in total, so to speed this up, I'm going to put a breakpoint here and tell it just to go and program all of memory for bank 1 of main memory. Okay, the breakpoint's been set. I'm I'm going to navigate 0x3 FFF. It's up to go, and as you can see, it's essentially all 0 1s as intended. And this is for from hex 20,000 to hex 3 quad F. And once this goes through, the function continues and the process repeats successfully. This completes the video for proving the memory is being written to bank 1 for all 32 sectors successfully. Thank you for your time.